An introduction to logarithms. Suppose you wish to invest $19,500 into a CD with an annual interest rate of 1.85%, compounded continuously. How long will it take for your investment to grow to $22,000? So this problem, usually we're trying to find a final amount, and we use that PERT formula, meaning A of t equals P times e raised to the RT power, where A of t is your final amount after t years have passed. Your P is your initial investment or initial amount. Your R is your annual interest rate, and written as a decimal, and then T is your time in years. So when we take a look at this, filling in all those blanks, we have 22,000 equals 19,500 e raised to the 0.0185 t. Now, the big difference is t is up in the exponent, and we don't have any tools just yet to solve for that. Usually we're solving for the part where the 22,000 appears, so this might be a little bit trickier. So we need to reverse the process of what we were doing before. Rather than finding a final amount, we want to find the time it takes to get a final amount. So reversing that process, we're going to need some new tools. So the new tools that we'll actually look to, we need some properties of the function e to the x. So when looking at e to the x, we have the graph of this function. If you notice, we can take a horizontal line and kind of pass it on up. And notice it's only hitting the curve at most once at any point in time as we kind of scale this on up and approach here. Well, what that means is that this function is 1 to 1, and more importantly, that means an inverse exists. So, with an inverse existing, we know we can reflect it over the line y equals x, basically reversing the x and y values roles. So if the point AB appeared on the original curve, the point BA would appear on the inverse. So that means the inverse, we can draw it quite easily, and this is given a special name. Actually, we have a couple of different ways. So right here, right now, we'll denote the inverse function by this log with a base e of x, and this one's actually a special type of logarithm. We'll actually later call this the natural logarithm because e occurs so often. It's a common logarithm here. So what do we know about this information? Well, we know the domain of the function f of x equals e to the x is negative infinity to infinity, and the range is 0 to infinity. And so all we did is we reversed the roles of the x and y's. So that means when we look at the inverse function, the inverse function has the domain that should associate with the range of the original function. So that means the domain, as you can see in our image here, should be 0 to infinity, and the range should be corresponding to the domain of the original function, so that should be negative infinity to positive infinity. Okay, so we have an idea of domain and range. So if b is greater than 0, and that's a real number not equal to 1, then y equals log with a base of b of x, if and only if b to the y equals x. So we have this interchanging of x and y's roles. That's essentially what we're looking at here. So let's try and see if we can write some of these logarithms in their equivalent exponential form. So we have y equals log base 2 of 16, a equals log base 3 of 1 over 27, and z equals log base pi of q. So if we start on the first one, notice we have log base 2 of 16 equals y. So that means if we look at that property up at the top for our definition, that means our base, which is 2, we should have 2 to the part that appears on the left-hand side, so 2 to the y, and it should equal what's inside the parentheses, which is 16. So we get 2 to the y equals 16 for that first one. In a similar manner, we'll get 3 to the a equals 1 over 27. And for our third one, notice pi is now our base, so we get pi to the z power equals q. Now, let's see if we can actually calculate these logarithms. So we had log base 2 of 16 in the previous slide, and we also had log base 3 of 1 over 27. Let's see what these values are. Can we use our ideas of exponential equations to solve these things? And the answer is yes. So if we start, we'll call it actually equal to y. So y equals log base 2 of 16. Did we have to call it equal to y? No, you have all sorts of options. But this is equivalent, as we saw previously, to 2 to the y equals 16. And now we want to write 16 as 2 to some power. Well, 16 is just 2 to the fourth. So what that means, we have 2 to the y equals 2 to the 4th, and so y must equal 4. In other words, if we go back to our original, we have log base 2 of 16 equals 4. Okay, moving forward on the next one, this will be a bit trickier. So we can start with the same thing, y equals log base 3 of 1 over 27. Once again, you can call this any other variable, but this allows us to convert to the exponential equation that we might be more familiar with. So this means 3 to the y equals 1 over 27, which 1 over 27, we can write that as 1 over 3 cubed. So you have 3 to the y equals 1 over 3 cubed. You can pull that cube since 1 over 3 cubed is the same as 1 cubed over 3 cubed. We get 3 to the y equals 1/3, the quantity cubed, and that is just 3 to the negative 1 on the inside there. So instead of 1/3, write that as 3 to the negative 1. Laws of exponents, we can multiply the negative 1 and 3 to make negative 3, so you get 3 to the y equals 3 to the negative 3, and we have y equals negative 3, meaning our log base 3 of 1 over 27 equals negative 3. Okay. So some of the logarithms that show up over and over again are log base 10, because 10 to a given power, that actually is an easy calculation, and we use that quite frequently. So what we do is we drop that base of 10 and we just write log of x. And the other one is log base e. That's used a lot in finance, exponential rates of decay, and things like that. Anything that's compounded continuously, essentially. It occurs so often we want a shorthand notation for that as well. And so what we do is, this looks a little funky, you'll have this ln of x, that stands for a log with a base e, but what we actually say is we call that the natural log of x, or natural logarithm of x. Okay, so let's try some calculations with these. So we have the natural log of 1 over e to the 6, we'll do the log of 1 million, and then we'll do the natural log of 100. So we'll begin with our first problem of evaluating natural log of 1 over e to the 6th, and we set y equal to natural log of 1 over e to the 6th. And remember, this natural log, that's just log base e. So we'll write this as log base e, and we'll kind of simplify the inside there. 1 over e to the 6th is the same as the quantity 1 over e raised to the 6th power. So now we can use our properties of exponents. We get e to the y equals the quantity 1 over e to the 6th. And 1 over e we can just write as e to the negative 1. So you have e to the y equals e to the negative 1, that quantity raised to the 6th power. You can now multiply exponents on the right hand side to get e to the y equals e to the negative 6. This implies that y equals negative 6, and so we have our natural log of 1 over e to the 6th equals just negative 6. So moving on to the next one, notice when we do not see base there, this is just a log base 10. So we start by setting this equal to y, and to simplify this, we'll write y equals log base 10 of 1 million is just 10 to the 6th power to make things simpler on ourselves. Now use those properties of exponents. We get 10 to the y equals 10 to the 6th. That means y equals 6, and we have our log of 1 million equals 6. So last but not least, we have our natural log of 100. And so notice that this is the same thing as y equals log base e of 100. So that means e to the y equals 100. But notice, really we aren't going to get any nice power of e to the y to equal 100. So it's going to be some funky number. Well, in order to do this problem, we're going to actually use the calculator. So we'll pull it up right here. And once we have that calculator in place, all we need to do is hit the ln button that you see right here, and then we hit 100 and close off our parentheses. And after we hit enter, notice that we get 4.605 and some other values. So we'll just round this, say 4.61, and that's our approximate answer for the natural log of 100. And this is going to be at our disposal. The calculator can do the log base 10 and the natural log quite easily with the buttons that appear on here. Okay, so now we want to actually go back to the real reason we were looking at these problems. So suppose you wish to invest $19,500 in that CD. We had the annual interest rate of 1.85% compounded continuously. How many years will it take the investment to grow to $22,000? So looking at the problem, we had the setup. We had 22,000 equals 19,500 e raised to the 0.0185 t. moving forward, how do we actually tackle this if we're looking for time? Well, first thing we'll do is actually divide both sides by that 19,500. And so notice we now have this written in the form that we can use our definition of logarithms, right? We can write this as a log base e of 22,500 over 19,500. And that should equal whatever's up in the exponents, so the 0.0185t. So notice we have that log base e of 22,500 over 19,500, and then we have our all equal to 0.0185t, and this means we can write this log base e with our common logarithms as natural log. So we have natural log of 22,500 over 19,500 equals 0.0185t. Now keep in mind we're going to be able to solve for t here, and the way we do that is divide both sides by the 0.0185, and what we get is something that we can punch into the calculator once again. So we can pull up our calculator and we can hit our natural log button, and then we want 22,500. We want to divide that by 19,500, and we're going to take all that whole quantity and divide that by 0.0185. After we hit enter, notice we get 7.735, or in other words 7.73 or 7.74. Really it's not going to make much of a difference since we're looking for years. How many years will it take? Well, notice you need a little bit longer than 7 years, so it'll actually be 8 years when we're looking for our investment to reach that desired amount.